morning everyone. So today is my first lecture based on a topic that is optical communication, and the subject code is BEC 057. So we are going here to discuss our first lecture, that is optical fiber link and ray transmission theory. So as you are a BTech student, so you already read about some communication based subjects like communication engineering or analog communication. So the concepts are same more or less, but here the channel is different, because in communication engineering whatever the data we send, it's through coaxial cable, but in optical communication we have a medium which is called optical fiber. So here we will discuss about optical fiber link and ray transmission theory, how the light will travel through this optical fiber at the end of the fiber, so that it will be received at the destination properly. So what are the topics we covered here in this lecture is brief history about the optical communication, what is the introduction to fiber optics, block diagram of optical fiber link, then its advantages and applications, and then the last total internal reflection, which is also called as TIR and Snell's law. So if we see the history of the optical fiber communication, so the first generation or the it will be operate near 800 nanometer, and these optical fibers are used gallium arsenide semiconductor laser, commercially available in 1980s, and it is a bit operated at 45 megabit per second, and here the repeater spacing is around 10 kilometers, which is larger as compared to that of the coaxial cable. So if you see how many repeaters are required in the first generation for optical fiber communication as compared to coaxial cable, it is far much greater, as you can see that it is 10 kilometers. In the second generation, the optical fiber operates near 1300 nanometer, where fiber loss is around 1 dB per kilometer. So we will discuss the losses in our next lectures. So losses are basically here attenuation. So typically it is around 0.5 dB per kilometer. So in this particular wavelength, that is 1300 nanometer, or you can say 1310 nanometer, the fiber exhibits minimum dispersion, or 1310 nanometer is also called as zero material dispersion wavelength. This is 1310 nanometer, which is also called as zero material dispersion. So it uses basically indium gallium arsenide phosphide, which is a quaternary compound semiconductor laser and detector. So in the lasers we have a continuous wave laser, and in the detectors we have a pin detector or a avalanche detector. Any detector you can use according to the application. So these second generation optical fiber will work in early 80s. By 1987, commercially available systems were operating at a bit rate of around 1.7 Gbps, you can see, and the repeater spacing is around 50 kilometers. So now the repeater spacing is much more higher as compared to the first generation optical fibers, that is around 10 kilometers. In third generation, fiber has minimum loss, which is around 1550 nanometer, and at this wavelength, that is 1550 nanometer, the dispersion is quite large. So we can easily reduce the dispersion by using the dispersion compensating fiber, which is called DCF. So this is a special kind of fiber, that is dispersion compensating fiber. So as the length of the single mode fiber, we can choose accordingly the length of the dispersion compensating fiber we can have, and it will cancel the effect of the single mode fiber dispersion, which is at 1550 nanometer. So the wavelength you have to remember that at 1310 nanometer there is zero material dispersion, but at 1550 nanometer there is considerably large dispersion. So it displayed more dispersion around 1550 nanometer, as I have discussed. So we can use dispersion shifted fibers could overcome this problem of the dispersion, designed to have minimum dispersion around 1550 nanometer. So these are also a special kind of fibers which shift the dispersion from one wavelength to another wavelength. In 1990s, commercially available systems were operating at around 2.5 Gbps. So from Mbps to Gbps we have worked from first generation to third generation, and it is capable of operating around 10 Gbps with single longitudinal mode lasers. So here the laser intensity is very high, at the beam is very narrower, as we have single longitudinal mode lasers Typical repeaters spacing here is much more greater as compared to second generation, which has 50 kilometers. Now we have repeater spacing around 60 to 70 kilometers. Now we have next the fourth generation optical fibers. So a main drawback of third generation optical fiber is that at 1.55 micrometer, the signal is regenerated periodically by using electronic repeater. So the fourth generation make use of the optical amplifier. So here the concept of EDFA comes, that is erbium doped fiber amplifier, which can be laid down in between the fiber length, and it is around 60 to 100 kilometers apart. So several WDM system, that is wavelength division multiplexing. So what is WDM? This is wavelength division multiplexing. So in wavelength division multiplexing, many wavelengths can be multiplexed and will be passed on to the single fiber. So here, because we require the amplification of each of the wavelengths inside the fiber, we can lay down erbium doped fiber amplifiers at a distance of around 60 to 100 kilometers. So several WDM systems were deployed across the Atlantic and Pacific Oceans during 1998 to 2001 in response to the internet induced increase in the data traffic. They have increased the total capacity by orders of magnitude. So we will have a much more greater, you can say, the data which we send from the transmitter side to receiver side in a bulk. So you can have a mix, many of the wavelengths which we can easily transmit from our laser to detector. So now we have a discussion on optical fiber, how the optical fiber have been made. So optical fiber is basically a long cylindrical dielectric waveguide. You can see from the figure, it has a core inside and a cladding outside, and next it has a buffer coating or a plastic jacket. So a long cylindrical dielectric waveguide, usually of a circular cross section, transparent to light over the operating wavelength, is the concept behind the optical fiber construction. So we can construct optical fiber through silica. Silica is the material, or it is called as sand. So it's easily available. It's available in abundance. So you can say that the cost of the optical fiber, or the length or the diameter of the optical fiber, is very narrower, or it's like a human hair, and the cost is also less because it's available in abundance. It is made from silica or a glass, you can write. So we have a core, we have a cladding. The core refractive index is much higher as compared to the cladding refractive index. So we suppose here the core refractive index to be N1 and cladding refractive index to be N2. So here N1 is greater than N2. Always the core refractive index is much higher as compared to cladding. So we have a solid dielectric of two concentric layers. We can say the inner layer, which is core of radius small a and refractive index N1, as I have drawn in the figure. Similarly, the outer layer, which is cladding, has a refractive index of N2. So for necessary, or you can say the total internal reflection inside the fiber will occur only when N1 is greater than N2. TIR is the principle inside the fiber. So we will discuss TIR in the later slides, how the TIR principle will work inside the fiber and how the rays will travel inside the fiber, having TIR or not having TIR. It depends upon the condition how the light is falling on the optical fiber. So light propagation through optical fiber. So as we have discussed that there is a core inside, and then which is having a high refractive index N1. So this is the core refractive index, and now the cladding, which has a lower refractive index as compared to core. So N1 is greater than N2. We have shown here that with the diagram that the fiber is bented, and the bent, you can say, when the light is totally internally reflected, then it will be easily passed from one end of the fiber to the other end. But if it is not follows the TIR principle, then it may get radiated from the core cladding interface and it gradually leaks out. So this particular diagram is showing that if the light is following total internal reflection, then no light will be lost. If it is not following the total internal reflection, then the light will be gradually leaks through the core cladding interface, which is shown here. So now we have a diagram showing how the light will be entered at the fiber and how it will get totally internally reflected inside the fiber, or it may get radiated away from the core cladding interface. So you can see that the light ray, that is the input ray. So this is the input light which is falling on the fiber, making an angle, some angle with the core axis, that is around theta. So suppose this is the core axis, it will make angle, some angle, that is theta I. Similarly, it will make an angle theta 2, or you can say theta 1 is here and theta 2 is here, making an angle theta 2 with the core axis inside the core. Then it will pass through the core cladding interface and reflected back into the same originating medium, that is the core. And now you can see that there is total internal reflection, and maybe some light will get radiated away from the core cladding interface. It depends upon the angle at which you are falling the light. If theta 1 is the angle at which the TIR will occur inside the fiber, then only TIR will occur. Otherwise, it will not occur, and it will have the light radiated away from the core cladding interface. So for light propagation through the fiber, the condition for total internal reflection should be met at the core cladding interface. It should be from higher refractive index to lower refractive index. So what is the need for fiber optic communication? So in long haul transmission system, there is a need of low transmission medium. There is need of compact and least weight transmitters and receiver. There is need of increased span of transmission. There is also need of increased bit rate distance product. So these are all the need which we have, which we require in the communication system. So basically with the coaxial cable, these needs will not be satisfied. So with the help of the fiber optic communication, we can easily have low transmission loss medium. We can easily have less weight transmitter and compact weight transmitters and receivers. We can easily have increased span of transmission and also have a bit rate distance product, which is usually increased in case of fiber optic communication. So now we will discuss about the block diagram of the optical communication system. So in the optical communication or in any communication, we require three systems, three blocks basically. So the first one is the transmitter, the second one is the medium, and the third one is the receiver, or the second one you can say that the channel. So in the transmitter section, we have the message origin, we have the modulator, then we have carrier source, then we have channel coupler. In the receiver side, we have the optical detector, we have the amplifier, we have the processing units, and then message output. In the channel or in the medium, we have the repeaters, which we have usually discussed, that the repeater spacing from the first generation to third generation, how it will be increased. And then there is a optical fiber. So in between the optical fibers, we have repeaters also at every 50 to 100 kilometers. So what is the purpose of this block diagram basically? How the light will be traveling inside the fiber. So at the initial stage, the message is in any form, that it can be a text or it can be a video. Firstly, the message should be converted into an electrical form. So you can do this process. The message can be converted into electrical form through any transducer. So any form of message easily converted into electrical form, and then it will be modulated through a laser or a optical source, which is basically here a laser source. So this is the carrier source, which is here a laser or LED you can use. So these two type of sources we use in optical fiber communication system. Then we have a channel coupler which couple the light to the optical fiber. So from the laser or LED, we usually get a light. So here we have a light. Before the modulator, we have an electrical signal. So the light will now transmit through the optical fiber using various repeaters in between the optical fiber to increase the signal level. We receive the light at the optical detector. So here light is received at the optical detector. Now optical detector, what it will do? It will convert the light or the optical signal again into the electrical signal. So from at this point, we will get an electrical signal. So now this electrical signal can be easily amplified, because in electrical we have different things, different boxes. We can do amplification, we can do filtration and other things. So we can easily do amplification after the electrical signal, we can have filtration after the electrical signal, and we usually get our message output in the form which we have transmitted. So this is the overall block diagram of the optical fiber communication system. So what whatever I have discussed, that is written here in the points, that is modulator. It converts the electrical message into proper format. It impresses the signal onto the wave generated by the carrier source. So this is the modulation part. Now the carrier source generates the wave on which the information is transmitted. This wave is called carrier wave. And now next we have channel coupler. It feeds the power into the information channel, which is here we have the information channel, that is optical fiber. The channel coupler design is an important part of the fiber because of the possibility of the high losses. So whatever the coupling between the light and the fiber is much more important, because if it is not easily properly coupled, the light is not properly coupled to the fiber, the light may get lost. So we have to see the proper coupling of the light to the fiber. Next we have optical detector, which converts the optical signal again into the electrical signal. And next we have amplifier and processing unit. So after the receiving the electrical signal, further amplification, filtering we can do, and we can get our desired output message signal. So what is transmission sequence? So information is encoded into electrical signals. Electrical signals are converted into light signals through optical source, and then driver, which is optical driver. Then light travels to the fiber. The fiber can be a single mode fiber or a multi-mode fiber. We will discuss in the next lecture. Detector converts the light or optical signal into electrical signal, and then electrical signals are decoded again into the original information. So this is the proper functioning of the block diagram, which is written here in points. So now we will discuss about the spectral band, optical spectral band. So there are various optical spectral band in the spectrum. So the International Telecommunication ITU has designated 6 spectral bands for use in optical fiber communication. So initially it has the O band only, that is the original band, which is having a wavelength 1260 to 1360 nanometer. Then we have E band, which is called extended band, which is 1360 to 1460 nanometer. Then S band, which is called short band, 1460 to 1530 nanometer. Then C band, 1530 to 1565 nanometer, in which the WDM will work. So in C band we have WDM or EDFA. Then L band, which is long band, which is called as long band, and it is around 1565 to 1625 nanometer. And then U band, ultra long band, which is 1625 to 1675 nanometer. In this bands, dispersion shifted fibers will work. O band was the original, which I have told you, which is used for single mode fiber links, and it can be extended into E band for fibers with lower water content, that is hydroxyl ion content. Lower water is basically OH ion content. S band consists wavelength shorter than C band but higher than E band. C band is the wavelength region used for conventional erbium doped fibers or WDM. L band is the longer than C band. In this longer wavelength, the gain decreases steadily to 1 at 1625 nanometer. U band is the region beyond the response capability of an EDFA. So you can see from the diagram, we have the power and telephone, then radio waves, then microwave waves, then infrared, then UV rays. So the optical range is in between 10 to power 9 to 10 to power 14. So you can have a laser communication in infrared region, that is around 10 to power 14. This one, 10 to power 14. Below the infrared region, there is microwaves. So it is having very high frequency. That's why the wavelength is very less, is in nanometers. So fiber optical work around around 10 to power 14 hertz, or you can say in terahertz, and the wavelength is around from 800 nanometer to 1600 nanometer. So what are the advantages of optical fiber communication? It has larger potential bandwidth. As I have discussed, the range is from 10 to power 13 to 10 to power 16 hertz. So it is potentially great potential transmission bandwidth than metallic cable systems. Therefore, the information carrying capacity of the optical fiber system is superior to coaxial cable. Small size and weight, optical fiber has very small diameter, which is equal to the, you can say, equal to the diameter of the human hair. Small size and lightweight property of an optical fiber is somewhat advantageous in various applications like aircraft, satellites, and even ships. Electrical isolation is the third advantage. That is, optical fibers which are fabricated from glass or sometimes plastic polymer are electrical insulator. They do not exhibit earth loop and interface problem. Hence, no hazards of short circuit as in metal wires. Immunity to interference, it is immune to electromagnetic interference and radio interference. Hence, operation of an optical fiber communication system is unaffected by transmission through an electrically noisy environment, and fiber cable requires no shielding from EMI. So, it is usually immune to electromagnetic interference, crosstalk, radio interference, etc. Signal security, you cannot easily extract the signal in between the fiber. It has high signal security. Low transmission loss, it has low transmission loss around 0.2 dB per kilometer, and this feature has become a major advantage of optical fiber communication. System reliability and ease of maintenance, the low loss property of the optical fiber cable reduces the requirement for intermediate repeaters or inline amplifiers, and hence with fewer repeaters the system reliability is greatly enhanced. Hence, reliability reduces its expenditure on maintenance also. Ruggedness and flexibility, if you can bend the fibers, it has a very high tensile strength, it has quite a small radii, and it can be easily twisted without any damage. Low cost and availability, the fibers are made from silica which is available in abundance, hence there is no shortage of material and its cost is very less. So, optical fiber offer a very low cost communication. So, these are the applications: military applications, medical applications, undersea cables, control systems, factory communications, railways, communication networks, etc. So, these are some applications of the optical fiber communication. So, now we will discuss here the Snell's law and the total internal reflection. So, what is a Snell's law? So, when the light is radiated, or you can say the light is hit from one medium to another medium, the interface between the two mediums. So, the first medium is N1 having refractive index N1, which is very higher as compared to the second medium. So, this is high refractive index and this is less refractive index. So, the light is traveling from the denser medium to rarer medium. So, the light is making an angle theta 1 at the denser medium and making an angle theta 2 at the rarer medium. So, you can easily see that the light is incident at an angle theta 1 and it is reflected away from the normal in the lesser medium or in the denser rarer medium, making an angle theta 2. So, when you increase the angle theta 1, it will come out to be parallel to the interface between the two dielectric medium, and when you more increase theta 1, it will get reflected back into the originating medium. So, now we have principle of light propagation through TIR. So, you can see from the three figures here, the first figure shows the light is incident at an angle theta 1 and refracted away from an angle theta 2, and there is some partial reflection at an angle theta 1 inside the originating medium. The light should be moved from denser to rarer medium. This is a necessary condition. In the second figure, the light is making an angle theta c, which is called as critical angle. So, here theta c is the critical angle. And the light will get refracted away from the normal, and it will be parallel to the interface between the two dielectric medium and making an angle 90 degree with the normal. So, here theta 2 becomes 90 degree. And in the third figure, we have angle which is much greater than theta 1, and now the light will come back to the originating medium, and this process is called total internal reflection. So, when you increase the angle beyond theta c, which is critical angle, the light will get reflected back into the same originating medium. So, here refractive index, what is refractive index? Refractive index of the medium is defined as the ratio of the velocity of light in vacuum to the velocity of the light in the medium. So, propagation of the light within an optical fiber is explained through two models. Basically, we have a ray theory model and we have wave theory model. Here we are discussing only the ray theory model. So, a ray of light travels more slowly in optically dense medium than in one which is less dense. When a ray is incident at an angle theta 1 normal at the surface of interface between two dielectrics of refractive indices, that is glass and air. You can have glass or air. Glass is having a high refractive index as compared to air. Reflection occurs. So, as we have discussed in the diagrams itself, then the light will travel from denser to rarer and it will refracted away from the normal and making an angle theta 2 from the normal. So, in the second case, we have critical angle. So, when theta c, which is critical angle, or theta 1 is equivalent to theta c, in this case theta 2 becomes 90 degree. So, we have Snell's law, that is N1 sin theta 1 is equivalent to N2 sin theta 2. When you put in this formula, what you will get, N1 sine theta 1 is equivalent to N2 sine theta 2, and so here N1 sine theta C is equivalent to N2 sine 90 degree, or theta C is equivalent to sine inverse N2 by N1. So this is particular theta C is your critical angle. So if you increase the angle theta 1 greater than theta C, then TIR will occur. So this is the whole process. Thank you so much. So this is the basics of the optical fiber communication. What is the optical fiber block diagram? What are its advantages, application, and how the Snell's law will work inside the fiber.